get going with the introductions now. So this is a proxy primer through the SGP. Most of our proxy primers are focused on specific geochemical techniques, but once a year we try to broaden out a little bit more and think about kind of broader approaches in geology or geochemistry that we'd like to learn more about today. And today specifically on Bayesian approaches to stratigraphy. And so most of our analyses in SGP have to do with changes through geological time or through paleogeography. And so this fundamentally comes down to the rock record and how we date and correlate samples. And so today, these are two approaches that can help us do a better job at that. Most people here are familiar with this, but SGP is an open research consortium dedicated to aggregating and analyzing geochemical data through Earth history. Please check out our informational website or search website. And if you're not involved with the project, we would love to have you be involved. The proxy primers are basically a series where we can hopefully accessibly learn about the basics of some geochemical proxy or method, today being Bayesian approaches to stratigraphy in a broad audience. This also creates a series of videos that we'll have available on our YouTube website that you can use as research or teaching materials. And finally, providing an open space for interaction with experts on each proxy. And so today we are going to have Tianran Zhang talking first. We'll then have a bit of questions on hers before moving on to the folks from Durham, having a bit of questions on theirs, and then having open time for discussion on these topics. In terms of our 2024 schedule, we had one proxy primer from Kim Lau already. We are now here today on the Bayesian approaches. The date that I'd like everyone to keep in mind is this October 9th date. We're going to have an update call for our phase 2 data product, working group updates, and how we're doing changes to the website. I'm really excited about some of these changes we're pushing through in terms of visualization, both with our developers and with our colleagues at the MacroStrat project that we're excited to show you. And then moving on to November, we have one more proxy primer on strontium isotopes. Okay, so with that, I'd like to introduce Tianran Zhang. She is a PhD student at Dartmouth College. She did her undergrad at Colorado College working with Paul Myro before moving on to Dartmouth to talk about or to work with Justin Strauss. And today she'll be teaching us about subsidence modeling with a specific example from her work in Svalbard.
Thank you very much, Eric. Let me just figure out the screen sharing situation. Sorry. So if
that looks good. Yep.
That, are you seeing the presenter's view right now, or?
No, we're seeing the correct view.
Perfect. Awesome.
Yeah.
Okay. Cool. Well, thank you all for coming again, and thanks, Eric, for inviting me and for the nice introduction. So today, I'm delighted to be presenting some of my research on substance age depth modeling using a Bayesian approach. And before I begin the content of my talk, I just first want to shout out to my advisor, Justin Strauss, and Brendan Keller, who has been really crucial to this whole project, and I could not have achieved any of this without them. So shout out to them. And just to briefly outline what I'm going to be talking through in the next 20-25 minutes. So I'm going to first walk through some of the motivations, which is going to be very quick and obvious for most people here. And then I'm going to walk through sort of the whole, the entirety of my model design, which is partially the substance modeling part, and then the Bayesian statistics part. And because I'm going first today, and so hopefully I can give you a little bit of just a quick introduction to Bayesian statistics, and so that I can pave the way to the second talk. And then finally, I'm going to talk through the case study that I did on the northeastern Svalbard Tonian succession using my model. And so for the motivation side of things, I think, as Eric already touched on this in the introduction, in order to gain a better understanding of the sedimentary record in general, we always hope to anchor our analysis with age constraints, hopefully like good age constraints. But as we are all aware, it's simply impossible for us to date every single horizon that we care about that are, you know, geochemically important. So here on this slide, I'm just simply showing a figure that basically summarized all the existing absolute age constraints up till 2020 for the Ediacaran. And even just from that simple figure, it's quite obvious that even for such a crucial time period in Earth history, we still have a lot of gaps in our time scale. And so this issue, I'm showing the Ediacaran because this issue becomes more prevalent in the Precambrian, because unlike the Phanerozoic, we can't really rely on biostratigraphy too much for relative dating. And so this is basically the strongest motivation for all that I've been doing. And but if we delve into this question a little bit deeper, so let's imagine for a given succession, this is what we're likely to run into in the Precambrian world. We're likely dealing with a situation where we have a thick succession, but only a handful of age constraints to work with. And so the problem becomes figuring out how time is distributed in between these these absolute age constraint points, because you know, again, the horizons we care about might be in the middle, and we don't really know how to get there in terms of the age. And so the traditional way, I guess the more traditional way in Phanerozoic is to basically linearly interpolate between the nearest two ages. This basically assumes constant sedimentation rate, which is not always true for real environments, as we all know. And so, you know, time might be not linearly distributed within certain sedimentary successions, or sometimes they can have huge variations in sedimentation rate, having moments of very fast deposition and then non-deposition for a long time. And so basically the core of my problem is trying to like find a way to better to do a more geologically accurate job of capturing this age depth relationship in an Asian deposit. And the approach I'm going to be taking is to zoom out and think a little bit more big picture processes and think about what controls this whole process of sedimentation. Because sedimentary rocks are deposited in sedimentary basins, and basins are basically created that's the next slide. So basins are basically created under different tectonic settings, which have different rates at which combination space is created. And so our understanding of the tectonic setting can basically provide some control on the rate that the whole sedimentary succession is deposited. And so basically this approach is generally called subsidence analysis, and that's what I used for my age depth model as the backbone of my age depth model. And before I jump into the details of that, I just want to quickly point out that this approach had this general approach of using subsidence analysis to figure out the age depth relationship in a sedimentary succession has been used successfully in some Phanerozoic basins and shown some promising results. This is just one of the classic papers by Bond et al. And this is just one of the many examples of that utility. And what I'm trying to do is I basically created this new program called subsidencron.jl, which is built in the Julia environment. And basically it is taking that classic approach from the physical modeling point of view, but adding in uncertainties. And the way I'm treating uncertainties is through this Bayesian framework. And so this is kind of how I characterize my model. This is a program that basically performs substance HDEF modeling for a very specific subset of sedimentary basins. I'm particularly looking at post-rift thermally subsiding basins that basically my model will be able to introduce and propagate uncertainties under this Bayesian framework. And just want to point out that this work has already been published. Here is the information, and you're more than welcome to check that out. And but here I'm just gonna quickly highlight sort of what my model entails and what it can do. And so so basically the next few parts, I'm going to be focusing on the two underlying part of this statement. So first walking through the substance HDEF modeling part, and then going back to the Bayesian framework, and hopefully give you a little bit of introduction on Bayesian statistics. And so in terms of thinking about substance modeling, I'm going with the classic McKenzie style model, which is an instantaneous rifting model that is uniform rifting all throughout the lithosphere. It is obviously simplified, like just within that sentence, there are a few assumptions that you know, in the natural setting it might not hold true, but we think it's a good first start, and is generally a good approximation of what you expect to see in a rift setting. And so basically in the McKenzie model, it states that in the rift basin, you basically have two stages through its lifespan. And so the first stage would be the syn rift stage, where you're rifting, laterally stretching this whole lithosphere by some factor of beta. And so what you create at the end of that will be a basin that has amount of substance that is caused by this lateral stretching just from the thinning of the lithosphere. And so at the end of the syn rift phase, what you will create is basically a upwelling of the asthenosphere at the bottom, which would mean that the asthenosphere, it's not at its natural state, it's not as its equilibrium. And so naturally it will want to drop back down to its original state, and that creates more substance at the top, at the surface in our basin. And so that basically constitutes the stage, the second stage of the rift basin evolution, where you see this post-active rifting phase of thermally driven substance happening in the basin. And so at the end of the lifespan of the rift basin, you basically see that the combination space created in the basin is in part the syn rift substance, and in part the post rift thermal substance. And basically the way we use substance modeling to get to the HDEF modeling part is to look at the thermally subsiding phase, because just by just through mathematical modeling, on the left-hand side, this graph, you can see that basically tectonic substance, which is substance solely driven by tectonic forcings, has this exponential decay relationship with time since the end of active rifting. And so this will be the part that drives my model, essentially. So in my model, I'm basically asking the model to create HDEF paths that mimic this shape of post-rift thermal substance. And so this is sort of very quick introduction. I know, like, I don't want to delve, just want to be here for too long to bore you all, but this is basically what goes into the substance cron.jl program, where the first part is just going from the current state lithology to that tectonic substance. And so a bunch of calculation that I have not described, but basically that's the decompaction, backstripping, all following sort of the classic way of calculating them. But also the new thing that I added to my model is to incorporate all the lithology dependent uncertainties into this whole scheme. And that incorporation is through the simple resampling, the Monte Carlo method. And so at the end of that, I basically get the tectonic substance with uncertainties, and then that tectonic substance with uncertainties will be plugged into the second part of the model, where I also introduce age constraints to the whole thermally subsiding part of the succession. And basically, this part is where the Bayesian framework comes in. So I basically take this general approach where the simple assumptions that I'm making for this part is only that I'm only assuming stratigraphic superposition and not assuming anything about sedimentation rate. And through that, and through the input of the age constraints, through the inputs of tectonic substance, I'm able to use this Bayesian framework to basically come at the Beth path, the Beth age depth path that fits my age constraints and fits this thermally decaying shape of tectonic substance versus time. And so what exactly is going on in this Markov chain Monte Carlo part? What exactly is going on in this Bayesian part? That's where I'm going to go in for the next step. And so I'm going to move away from my model now and like briefly talk about just Bayesian theories in general. And at the end, I'm going to bring it back, and hopefully that makes more sense for understanding this model. And so before this looks a little bit complicated, but before I delve into the equations, two things that I want to point out before we just go into any detailed explanation is that it's basically what I see as two of the more important things in like Bayesian way of thinking. The first is that from now on, in the Bayesian sense, what I'm referring to as probability will be basically expressing a degree of belief, not in the frequentist sense that we are more used to, the more objective sense that we're more used to. And then the second point is that basically through this, the core, I in my opinion, the core of this Bayesian statistics will be the idea that our data that we input, that we observe, will be basically updating these beliefs, updating these possibilities. And so if I try to break down this equation that's here, it looks super messy, but let me just walk through. So basically what Bayes' theorem is basically what Bayesian statistics is all built upon. And so what the Bayes' theorem is saying is that the probability of, I'm here basically substituting the A's and B's with like hypothesis and evidence so that we can better understand what's happening. And so the probability of a hypothesis being true given the evidence is proportional to the probability of seeing the evidence if the hypothesis is true times the probability of the hypothesis being true. That is a mouthful, but in a more simple way of putting it, that is basically saying like, we basically, before seeing any of the data, we should have some kind of a background knowledge about our parameters. And then our parameters, that is one part of it. And then the other part is the data part. And so if you combine those two, you basically be updating your knowledge about the parameters, and that would basically be like the posterior. That's a very, very simplified, very short summary of what is happening here. But essentially, then these three components will have their own names. I'll be referring them from now on, but basically your background knowledge, the knowledge that you already have subjectively before seeing any data, that is called the prior. And then your sort of the function based on your data, that's going to be the likelihood function. And then what you come up with at the end of it, the updated knowledge based given the data, is the posterior. And just to note that the prior and posterior, they're both going to be in terms of distributions, just yeah, not having too many words on there, but just know that they're all in distributions. And so so then basically this is the general way of thinking, but then how to get here from actually getting that posterior, there are many algorithms to deal with that problem. And the algorithm that I chose to use is the Markov chain Monte Carlo algorithm. And basically that word can be straight up broken up into two parts. The Markov chain part essentially describes this process of basically your event only depends on the previous state, and that's that through that repetitive process you continue through this chain. And so like the example that I will give will be the game of Monopoly, where basically where you're at a certain given moment will basically just be determined by your previous location position on the board and the number that you roll on the die. And so the Monte Carlo part of this algorithm would just mean repeated random sampling. And so here's an example of a repeated random sampling. If you, for example, don't know the area of the circle, and the way you can figure that out is just by kind of randomly picking points in the square and count the number of times that you're in the circle versus the number of times that you're not. And that can basically get you the area of the circle through this repeated random sampling process. And so combining them together, again, there are a lot more specific algorithms out there that they all have different way of approaching this problem, but kind of a general workflow for working through a Markov chain Monte Carlo is that first we'll basically have, again, before everything happens, we'll have our prior beliefs about the parameters, and then essentially we're going to make a proposal that falls in this prior distribution, that proposal theta 0, and then basically after this initial proposal, we'll begin this iterative process where we'll make a small adjustment to that proposal and then calculate the likelihood of that second proposal after the adjustment, and then compare that likelihood of that proposal being true given the data with the previous proposal. And essentially there are, again, a lot of different criteria for, and a lot of nuance for how to figure out when to accept and when to reject. But sort of a general principle is that if your second proposal is going to have a higher likelihood, then you accept that proposal and then move to this second proposed point, and then basically make your adjustment from that point. If your second proposal is not better than the first proposal, then you basically stay at that first point and then make another adjustment from that very first point. And so going through this process iteratively, all kind of during every step, your likelihood is calculated based on your observed data. You eventually get to this distribution at the end that is going to be essentially describing your posterior distribution. And so here is just a little illustration of basically how you get there. And one of the things to note here is that your initial guess can be a very bad number. Essentially, it can be very outside of the posterior distribution. The model, because of this iterative process, and because it will move to the better point at each given point, the model will basically, after a while, figure out a better place to be at. And so essentially, if your guess is way outside of this range, after a while, it will come back to that place where you have the highest likelihoods, and then kind of stay in that range. And so basically that is creating the stationary distribution, as we say, after this burn-in period that we call it. And so the stationary period, what comes out of it will be the posterior distribution from the Bayesian. Did I get a question or something just now?
No, I think we're good.
Okay, cool. And so so basically that is sort of all, let's see. Yeah, that's the same. And so that is essentially what a very quick introduction on Bayesian statistics is. And so going back to my model, what you're going to see, the priors and the posteriors, for example, I'm setting I'm making assumptions about the timing of that transition from active rifting to thermal subsidence as one of the priors, and then I'm giving it I usually give it a very wide distribution so that I'm like encapsulating all the possible ages, and then through this iterative process, the model basically finds out the best path through that age step space, and then will basically spit out through each proposal. It will basically come with a proposal for the transition from active rifting to thermal subsidence, and then eventually, after stationary distribution is reached, I let the model run for a little bit longer, and then that distribution will be my posterior distribution, which will be the final result that I report. And so that is kind of the general rundown of my model. And now just with the little bit of time that I have, I'm going to go into the case study of Northeastern Svalbard, the Tonian succession in Northeastern Svalbard, where we actually use this model to try to generate an age depth relationship through this critical succession with very limited radiometric age constraints. And so for those of you who are not familiar with this succession, it is a very nicely preserved continuous succession of early Neoproterozoic deposits that basically record some of the important paleontological and carbon isotopic signatures. The details, I'll leave out the sedimentological details, but basically it has been proposed that the transition from active rifting to thermal subsidence is occurring at this boundary between the veteranum group and the academic green group. And so this is where I'm starting my model, and this is where basically through from the base of the academic green group to the glacial deposits, this is where I'm doing my age depth model. And I do want to point out that prior to my work, Harrison et al. Made this first attempt to apply substance analysis methods in Precambrian in general and generated an age depth model using the Mackenzie model. But our work is basically building on top of Halverson's work and made some modifications. First is that we basically incorporated and propagated the uncertainties associated with lithologies, and also in the second part were associated with the I guess the shape of the curve. And second, as had in my model design previously, and second, we added this treatment for the first part to get from the current stratigraphy to the tectonic substance. And so as a result, and another major difference, I guess, between our models is that Halverson et al. Mostly used correlated ages through chemostratigraphy, chemostratigraphic correlations, versus we basically only used local age constraints. And so we were able to get 4 age constraints. 2 of them are already published, and then 2 of them were publishing in our paper for the first time. And so 4 age constraints, with 2 of them being one-sided constraints, is not really that exciting. But we were able to just use these very few age constraints, generate age depth curve. On the left, this is kind of the tectonic substance curve through I guess again stratigraphic thickness, and then on the right is the age depth relationship through this whole succession. And through that we were able to find horizons of interest and make predictions, make age predictions. And so the next graph is going to be a little bit small to read, but basically we were able to find, for example, a few of the formation boundaries to make age predictions. And then we were able to generate age predictions basically for the onset and the termination of the Bear Springs carbon isotope excursion and the beginning of the Rosoya carbon isotope excursion. And one thing to note is that our uncertainties are significantly bigger than the Harrison et al. Study. We are consistently been getting like 10 million years to almost like 20 million years of uncertainty, while Harrison et al. It's mostly like a few million years of uncertainties. And that we contribute to the fact that we are only using local constraints, and the fact that we believe this is a better representation of the uncertainties that we're facing in this succession that don't have a lot of age constraints to begin with. And so this is, I guess I can stop right here. I have another like newer application of the model, but I'm happy to just stop right here and then answer questions.
Sorry. Thank you so much. I think that was a great introduction, and I really appreciated I think that was one of the most straightforward discussions of intros to Bayesian statistics that I've ever seen. So I really appreciated that.
Thank you.
Yeah. Why don't we take some questions? I just had a quick clarifying question. So if people are interested in using your program, subsidence.cron.jl, what are the basic input? If you could just go over what are the input parameters that people need, or what kind of data do they need in order to run that?
Yeah, of course. Thanks for reminding me of that. So basically, you first, it is all open source. It is a published package, and so you'll be able to find that information. There's like a step-by-step guide online, but basically what you need for the input is your stratigraphic succession, basically including the thicknesses of the layers. Layers meaning whatever resolution you want. It could be like a bed measurement. It could be, at whatever resolution you want. Basically, you just need like layers and their corresponding thicknesses and their corresponding lithologies, and then that would be the first part of the input. The second part of the input would just be kind of your existing age constraints and their uncertainties, and that uncertainty is on the two sides. One is on the age itself, so the analytical uncertainties or whatever you have on the age constraint itself. And also you'll be able to input uncertainty on the height as well. And so if you have correlated ages and you're not sure where exactly in the succession it correlates to, you'll be able to use that as a constraint as well. We just didn't choose to use it for just to test like the model performance, but that is one option. And so and the third component, which is the prior knowledge part that I was talking about, is basically you need to come up with a rough idea of the transition time from rifting to thermal subsidence. And so, and by the rough idea, I mean like I basically was inputting an age with like 50 to 100 million years of uncertainty. So that is possible. The model will narrow it down for you, and that is one, plus some prior constraint on the amount of stretching, which that can even go broader. Like we've been experimenting with kind of an uncertainty basically encapsulates like all the normal types of rift basins that you will see. And so that part is like, I feel like if the users don't know, they can just go with the model, like the preset values. But the more important, like I guess more individual individually decided model inputs will be the stratigraphy and the ages, and some guesses for the age of transition from active routine to thermal subsidence. Yep.
Great, thanks. It looked like we had a question from Jaden, if you want to jump in, and then we'll probably move on to the next talk, and then hopefully we can return to questions at the end.
Hello, really interesting talk. I was curious about the slide where you show the evolution of the initial guess
Yes.
into the actual fill. The curve that describes that transition appears to be pretty stochastic. Is that behavior typical of guess evolution?
Like this one, you mean?
Yes.
Yeah. So I would say that I would say first of all, you know, this scale, it's like it's pretty zoomed in, and so I like this is basically given the prior of 0 plus minus 1 as the 1 sigma, and then it's basically like for each jump you're gonna see it's like maybe like 1 to 2, maybe it gets to 3, but basically so the way I know my model is set up at the moment is that you're jumping from a point which is for a certain guess, if I'm remembering this correctly, you're basically multiplying your sigma with a random number from the distribution of center on 0 with a sigma of 1. Basically, so like for each step it would jump that much, but then if you like, because basically this whole process is performed on multiple parameters, and so if you combine them, then your likelihood term might jump a lot. But essentially, the current way of the model setup is not supposed to let you jump too much relative to your like your prior distribution, basically. And so yeah, it should be all relative at the end.
I see. Thank you. Thank you.
Great. Well, thanks so much. I am now going to jump on to our next set of talks. I'm excited to welcome some people from more the paleo community outside SGP who have agreed to talk. I saw Dr. Martin Smith advertise this program on the PaleoNet email list, and so I thought he would be great to get to come in and talk. So Martin Smith did his PhD at University of Toronto, working on Burgess Shale type organisms. Went on to do a postdoc at University of Cambridge, and has been a professor at Durham University in the United Kingdom since 2015. He'll be joined in this by Dr. Kilian Eichenseer, who did his undergrad and MSc at University of Erlangen before moving on to a PhD at Plymouth, and is now a postdoc at Durham. I just wanted to take a moment to highlight this paper that I've never met Kilian before, but I happened to read this paper during my sabbatical, and I wanted to highlight it because I think it illustrates some of the principles which I guess have been transported a bit from the paleontology literature into thinking about geochemical data. And this is a short paper, but provides a lot of good food for thought. And basically, they're modeling latitudinal temperature gradients from sparsely sampled climate records. And so what's shown here is where oxygen isotope records occur throughout the Phanerozoic. And you can see that in some moments, like the Ordovician and Silurian, they're basically at the equator. At other times, like the Carboniferous or Permian, they tend to be more focused at the poles. And if you think about a latitudinal temperature gradient, this is shown here for the Eocene and the modern. Of course, where your samples are going to affect what your overall bulk values are. And so they did a good job in this paper. Kilian has some other papers on the early Eocene in terms of thinking about how where you sample affects what you come out with. And this is the kind of approach that I really hope we can we can continue trying to apply to large geochemical data sets through time, like the SGP. So that was just a little introduction, kind of a tangent, but now I'd love to jump into Martin and Kilian telling us about their work and their R package.
Great. Well, thanks very much for the introduction. So I plan to tell you a little bit about our approach to stratigraphic alignment, and I'll give you a little setup as to a motivation that will include a few fossils, hopefully not too many, to sort of set the scene for what we're trying to do here. But I think the methods that we have very wide applications whenever we're thinking about correlating rocks and understanding what's going on behind the hood. So the particular problem that got me interested in this question is the Cambrian explosion, and I guess many of you are familiar with this transition from these amazing Ediacaran weird things in sites of exceptional preservation to the diverse set of animals we see in the Burgess Shale and similar deposits in the Cambrian. And we appreciate there's a fundamental transformation here in what life looks like on the planet. But these are sites of exceptional preservation. Is this really showing us what's going on? Well, we can look at various other modes of fossilization. So small shelly fossils are abundant in the late Ediacaran. They're simple tubes in the early Cambrian. This whole wealth of animal diversity appears. Could this be a taphonomic effect? Well, we can look at different preservational modes, like small carbonaceous fossils. And again, we see the same pattern of Ediacaran simplicity turning into a plethora of Cambrian forms from all sorts of complex animal groups. We see this in the trace fossil record. If we look at exceptionally phosphatized embryos, again, Ediacaran, simple blobs, early Cambrian, we see these amazing animals full of morphological complexity. So we have a very clear before and after view from these different fossil records, that something happened in the Cambrian. But what it's harder to determine is whether this was an explosive event, this sort of geologically overnight one-off evolutionary miracle, or whether it was just the first of many adaptive radiations. And if we look at an adaptive radiation later in time, it had the same dynamics. It doesn't look as exciting because it's not the first, so there are other things in the background. And to sort of resolve this dilemma, this dichotomy, we really need to know something about the timing of how the Cambrian explosion happened. And if we can tell something about the timing, then we can start to say something interesting about what environmental factors might have caused it. Did biology lead evolution, environmental change, or did environmental change lead evolution? But this is a kind of difficult thing to untangle, partly because although we have all of these different fossil modes, they occur on different continents at different times, and they're often on different continents to our absolute age constraints. So it'd be very hard to line up actually this evidence that we have from different deposits around the world. And that's made more challenging still by this problem that Tianran alluded to, that in these early rocks, we don't have a good biostratigraphic framework. We can't use fossils to join the dots because they're so sparse. So how do we actually link together what's happening when on different continents? Our best bet for doing this at the moment is probably delta 13C ratios. If we assume, and it's maybe not an awful assumption, that the Cambrian Ocean was broadly homogeneous in its delta 13C composition, we can hope that if we see excursions here in the world, we're going to see that same signature at other sites. And we can use this signature to match up the wiggles and match up our sites from sequences that are carbonate rich. And this is quite a lot of work. Fred Boyer and many others have worked on this problem and put an awful lot of thought into these different sections and how might they line up. And really the state of the art seems to be just staring very hard at these things and doing this by hand, and it's incredibly time consuming and somewhat subjective, but it can be done. But even when you put all this time in, it's not always clear that there's one best solution. So this is a recent compilation where we get these Cambrian to Ediacaran successions, and there are maybe 3 different ways that you can realistically line up these delta 13C values. And so these look a little bit similar, but just to sort of highlight, here's one particular horizon that might be of interest, this 1N, and the position of this horizon is off by about 5 million years in these different models. was crossing this potential position of the Ediacaran Cambrian boundary. So that's quite a large uncertainty. And we've no real way of knowing, well, which of these is the best model and where really does this horizon line up? So it would be nice to be able to sort of put some numbers on this. And I was explaining this problem to a friend, to a colleague in archaeology, Andrew Millard. He said, this sounds very similar to the problem we have with Delta 14, with 14C, looking on archaeological timescales. We have these wheels, we have these curves of isotopic values, and we want to line them up and we want to know the uncertainty. And yeah, this is something that is not quite a solved problem, but Andrew and others have got very good mathematical solutions to doing this in a way that moves that subjective element back a little bit. So we started talking and saying, well, how can we use these Bayesian approaches on Cambrian, on deep time questions? and yeah, it's possible. So Kilian in a moment is going to take over with the details of the model that we built, but just to sort of capture, I guess, the key elements of the Bayesian approach. Tianran did a great job of spelling out sort of how this works in detail. I want to sort of flesh up the highlights, I guess, that are pertinent to the way we're using Bayesian statistics. So the first distinction, I guess, to highlight is that frequentist statistics that we used to these underlie p-values, t-tests, these sort of high school statistics, tell us the probability of seeing some data that we might observe given a model, which in some ways is not very interesting. We've seen the data. We're not as interested in the probability of having seen it. What we really want to know is what's the probability of a model, or a stratigraphic alignment in this case, given the data that we have actually already observed. So Bayesian statistics sort of inverts this to give us a probability that we're really sort of interested in. And yeah, by model here, we're thinking of a model of how rocks might be aligned, and some of the parameters of that model will include that stratigraphic alignment. So in principle, the Bayesian approach allows us to say, here's a particular alignment of two delta 13C signals, and I can give you a probability that this certain alignment has over this one. And we can start to compare different candidate alignments. So we've also used the Monte Carlo Markov chain approach, MCMC sampling approach, and the key feature to take home here is that we have some clever way of evaluating different proposals, different alignments in this case, and we end up with some sample, a posterior sample, that samples possible solutions according to their probability. So in this ball pool here, there's some true ball which has a colour, and that colour is probably equally likely to be red, green, yellow, and blue, and there's a very small chance that that colour is grey, and that's sort of summed up here by this one grey ball that shows this one low probability outcome that might still nonetheless be of interest. So if a feature shows up in 90% of our samples, that feature should have a 90% probability. And taking that approach and applying it to stratigraphic alignments then might allow us to say, well, actually, let's look at these three different alignments that have been drawn up, and maybe we can assign an actual probability to each of these separate alignments. And likewise, if there's a horizon of particular interest, the first occurrence of such and such a fossil, or this delta 13C excursion, can we assign a possible age, and not just say, okay, here's a number, but to assign some probability distribution to that age. So I'll hand over to Kilian, who can take you over how our model deals with this in practice.
Yes, thanks, Martin. Thanks, Eric, for the introduction. So the most important aspect that we have to solve if we want to evaluate. Oh, sorry. Hope you can hear me now. So if we want to evaluate the probability for different alignments, the most important problem to solve is how do we compare those alignments with each other. And the component that our model uses is fitting a cubic spline to all the data points. So here in this example to the right, we have data from two different sites, red and green, and this black curve is trying to fit both of them simultaneously. And you can see in some areas where both curves don't overlap very well, there's a lot of deviation. Whereas if we shift that green curve slightly upwards, the deviations become a lot smaller. And in the context of our Bayesian model, this better fit would translate to a higher likelihood. Now, this likelihood that will determine which of the models that we evaluate is the best can easily be expanded. For example, we might have radiometric dates as age constraints or tie points. In this example, if this black dot or black star in the red side corresponds to that star down here in the green side, we can, for each alignment that we want to test, we can calculate the height difference, and then the smaller the difference, again, the higher the likelihood of the model will be. Then with that component, we can now explore and compare different alignments. So we could either do that directly with pre-existing alignments that someone has aligned visually, or we can let the model do that for us by automatically trying various different alignments, and that's more convenient in practice. So here what we can do is, for example, try out different scaling factors for one section relative to the other. So scaling means we increase or decrease the sedimentation rate, which results in stretching or squeezing of the section. And in the simplest case, we would assume that the sedimentation rate is constant in the whole section, which is a strong assumption. We could also divide it into different parts and allow for different sedimentation rates in the different parts of the sections. Unfortunately, in this implementation, we cannot allow the sedimentation rate to vary between all the different points in practice, because there would be a lot of unknown model parameters that are difficult to estimate then in the model. And the second thing we can do is shift around the section to try out different alignments. Now, again, we use Markov chain Monte Carlo algorithms to try these different alignments and derive the posterior. So using different shifting and scaling factors, the second curve is shifted relative to the first one. And for each iteration, the likelihood is computed. And the parameter values of the shift and scale parameters are recorded throughout the sampling process. And we then get the posterior distribution, which is a distribution, probability distribution for every model parameter. And from that, we can derive the most likely alignments. It could be more than one, and also age models that give us age estimates for every height of the section. So that was just a broad overview, and this will now, well, I'll illustrate this with an example case study where we wanted to date the first Siberian trilobites. So they are of particular interest because in the Cambrian literature, it's often mentioned that the oldest trilobites might be from Siberia, but nobody is able to give an actual solid age estimate. It might be around 521 million years old, because presumably it's older than the Moroccan trilobites, but we'll try to do better here. And the data that we put into the model are carbon isotope measurements from 2 Moroccan sections in red and green to the left here, and then carbon isotope measurements from the Siberian section that also marks with this trilobite here the horizon where the first trilobites occur in Siberia. Additionally, we have radiometric dates. So you see that the red section here to the left is particularly well dated with 4 uranium lead dates with quite a low uncertainty. And then the other 2 sections only have 1 date each, and they have a lot higher uncertainty. So we will try to align those green and blue section to the red one using mainly the carbon isotopes signals, and then the dates from the red section should allow us to date the other two sections. And with that, the Siberian trilobite occurrence. In running the model, so can now see an example of the different alignments that the model tries. Now, we have to specify priors for the shift and the scaling parameters, and those will determine which alignments will be tried. So that can be very useful if we already have some pre-existing knowledge on sedimentation rates, for example. So here, let the model run. It tries a different alignment, still not very good, still a lot of deviation from the spline. And now it's looking to get better. You see that those sections start to line up. And if we let it run for long enough, it should converge on a most likely alignment or multiple likely alignments. And this can now be visualized. We can see that they lined up pretty well. And that was not us telling it exactly how it has to line up, but only giving the data and some broad constraints on the sedimentation rates. Here it also found an alternative alignment to the left, where the blue curve, the Siberian data, is shifted upwards a bit, and would then suggest somewhat younger ages. But almost all of the samples from that Markov chain Monte Carlo process were falling into that more likely alignment to the right. Now, from those alignments, we can now visualize the age models for each site. So here, there will be the first section, the red section, with height on the x-axis and then age on the y-axis. And here, the uncertainties, especially in the upper part where these radiometric dates were, are quite low. And also, we can see that the sedimentation rate changes a few times throughout because we allowed a couple of changes in that section. Second section, the age model comes with a lot higher uncertainty because that didn't have a lot of peaks and troughs in the carbon isotope curves. So there was quite some wiggle room in how it aligned it, and also only one date. And the Siberian section again has quite low uncertainties because the carbon isotope curve had a lot of structure, so that was able to align it with a lot of confidence to that Moroccan section. And taking that Siberian age model, we can now read off the age of specific horizons. So the trilobites were found at around 585 meters, or a level corresponding to that height. And reading that off gives us 520.4 million years, and yeah, with some uncertainty as well. And if we bring it together with the age estimates from other paleocontinents, so yeah, this is our Siberian estimate. We now have, are able to say it's most likely younger than 521 million years, and the age difference in the appearance compared to Morocco is probably at least 500,000 years. And if we apply this to other paleocontinents with a good carbon isotope record, then hopefully we can provide a more detailed picture of the asynchronous appearance of trilobites across the globe, which, yeah, putting uncertainties of a few 100,000 years only in between those appearances. And lastly, so we will soon release this method as an R package called Stratobase. Yeah, definitely this year. And the method is quite flexible, so it doesn't have to be Cambrian data. It doesn't have to be carbon isotope data. I think any quantitative signal from that has been recorded in more than one site, you could try to correlate it using the Stratobase package. And yeah, now I'm ready to take questions. Thank you.